Okay, folks, this is actually my second time through. I did this video, and for some reason the recording came out with me sounding like Charlie Chipmunk. So I'm not sure what the technical problems were, but hopefully this will be better. This is going to be a continuation of yesterday's lecture, and this is kind of a makeup for the snow day we had. Now, a couple of things. First of all, I'm not going to be pausing to let you write down notes, because what you can do is pause the video to take down notes. So that should make things much more efficient. So hopefully in about a 15-minute video, we'll do almost as much as in an entire class. Also, there are going to be a couple of examples. And for that, I would like you to do the same thing. I will ask you the question in the example, pause the video, try to do the example, and then continue on with the answer once you've gotten the answer. Or if you need just a little hint, then maybe you can proceed with the video just a little bit and get the hint and then continue on to the right answer. So at any rate, this is what we were talking about yesterday. We're talking about work done by a gas in a cylinder. And we said basically that the gas does work. We said the gas does work on the cylinder, on the piston, by expanding. And we go to from an initial to a final state. And so the thing is, there's plenty of different ways you can get from an initial to a final state. So we have P initial here on the left, and let's not use this as P final. Let's go to do the same P finals we have on the right-hand graph. So on the left-hand graph, we have a different process. So we have our P final here, okay, which is about the same as the P final here on the right. Okay, so the work that the gas does depends entirely on the process. And for example, if let's say we decrease the pressure at a constant volume like this, we go straight down on the PV diagram to the final pressure, and then what we do is we increase the volume at constant pressure, which is very difficult to do. You have to maintain the same pressure. You do that by adding heat. And basically when that happens, then the work done by the gas will be nothing more than P final times delta V, which would be this area underneath the line right here. Okay. The thing is, that's only one possibility. You could also, if you wished, go straight across with the initial pressure to the final volume, and then go straight down by cooling the gas, removing heat at a constant volume, and then getting to the final pressure. In that case, the work done by the gas would be much greater. It would be the initial pressure times delta V. So it would be this area under here. Okay. If you did it by just letting the gas expand naturally, then you would have a process similar to what you have on the right-hand side, where the pressure goes down from the initial to the final, and it depends on the pressure along the way. So you basically add up these little rectangles, or you do an integral and make infinitely skinny rectangles, and then the work ends up being the area under the curve. Okay, so as you can see, the gas can do dramatically different amounts of work. You could have this amount of work, which would be the least. You could have this amount of work, which would be a little bit more. Or you could have this amount of work, which would be the greatest amount. Okay, and it all depends on the path. The thing that doesn't depend on the path is the total amount of energy. Okay, because what happens is the work might be different, but the total energy difference is not different. U, the internal energy for the initial state, and U, the initial internal energy for the final state, are determined only by P and V. So we're going from a certain initial state to a certain final state. there's going to be a certain change in internal energy. It's a certain change in U. And that's going to be unique. So how do you compensate for the fact that the work could be different? Well, you compensate by using different amounts of heat. So the different amounts of heat is what really matters here. And that's going to lead us right to the first law of thermodynamics, because the first law of thermodynamics is all about conservation of energy. And since you're changing the internal energy by a given amount, you have to do it with exactly the same amount of energy. It's just that that energy can be divvied up into different types, either work or heat. Well, basically only two different types. So, work depends basically on the path taken. The work of the gas, by the gas, and on the gas for that matter, depends on the path taken. If you press down on the piston, you're doing work on the gas. So that is positive work being done on the gas. Basically, your work is transferred to the gas. So the gas gains energy when you do work on it. The energy of the gas increases. On the other hand, when you let the gas expand, it's the gas that's doing the work, and the gas then will lose energy. The system will lose energy. Just like you lose energy when you're carrying something up a flight of stairs, you're doing work, and therefore you're expending energy, you're losing energy. In the case of the gas, it loses this internal energy. The internal energy of the gas is less, and so expanding gases lose energy. If you compress a gas, those gases gain energy. Okay, so we've been talking so far about work done by the gas. The work on the gas is just the negative of that. It's just the inverse of that. Okay, just the opposite. So work done on the gas would be negative V initial, V final, P dV. And take note of this. The pressure, the dV, the delta V, if delta V if V final minus V initial is greater, is greater than 1, it's increasing in volume. If it's an increase in volume, then you have negative work done on the gas. You have an expansion. That's work done by the gas, basically. On the other hand, if you have a compression, if V final is less than V initial, okay, then delta V, your delta V basically is negative, then you have positive work done on the gas. So it's very easy to as long as you think about this in conceptual terms, it's very easy to understand this. If you're expanding, then you're losing energy. You have work done by the gas, but negative work done on the gas. If you're compressing, you're gaining energy. That's positive work done on the gas, negative work done by the gas. Okay, so you got to be very careful keeping the signs correct in the work done by the gas equations. Okay, so for a given state of beginning and end states, okay, which are unique values of internal energy, you have either more work and less heat, or less work and more heat. Okay, so as we went from that initial state to the final state, there was an infinite number of ways you could get from the initial state to the final state. But the point is, the work and heat together have to be the same, because you're changing the energy by a certain amount, and the total stays the same. So work plus heat remains the same. The total stays the same due to conservation of energy, because delta U, the change in internal energy, is going to be the same for any given set of beginning and end states. And so it doesn't matter how you get there, the total difference in energy is going to be the same. Okay. So in addition to work, the other thing you have to worry about is heat. Okay, so heat transfer in and out of a system depends on the process. Okay, but the work and heat transfer together only depend on the initial and final states. So that is the first law of thermodynamics in a nutshell. So let's formally work through and write down the first law of thermodynamics. Okay, so the first law of thermodynamics states that energy can be transferred in two ways. First, work done on the system, and secondly, heat added to the system. Okay, the example I gave last week is if you want to warm up your hands, there's two ways you can do it. You can rub them together and do work, or you could blow on them, which transfers heat from your breath to your hands. And both ways will increase the internal energy U of your hands. Okay, so the equation for the first law of thermodynamics, which you're going to be seeing a lot in the next week or so, is this. Okay, it's delta U, the change in internal energy, is equal to Q, which is just the heat, and W on, so the work done on the gas. And I like the way this is written because, if Q is positive and W on is positive, that increases delta U. Now the tricky thing is that integral we showed you a few pages ago, that is the work done by the gas. Okay, so when you're expanding, it's the work done by the gas. So the work on the gas is the negative of that. Okay, so if you want to put in that integral into the first law, what you have is the change in internal energy is equal to heat minus the integral V final, V initial, or V initial to V final, PdV. Okay, so the area underneath that curve, if you're going to the right, from left to right, is it's going to be negative of that. Okay, so again, keeping the signs straight, Q is positive for heat added and negative for heat lost. Okay. Work is positive for work on the system and negative for work done by the system. So when you're doing work on the system, when you're having a compression, then it's positive. When you're having an expansion, then work is negative. The work is done by the system, and so W on would be negative. And it loses, that basically the gas loses energy. Okay. So remember, this is conservation of energy. Also, heat is a microscopic quantity. You can't see it, you can feel it, but you can't see it. And work, on the other hand, is a macroscopic quantity. You can see when it's being done. You can see a piston being pushed down. You can see somebody rubbing their hands together. Okay? Whereas when you put your hands next to a radiator, you can't see the heat being transferred to your hands. All right. So let's do a little example, a very simple example to start out with. Okay. A gas is heated with 300,000 joules and allowed to expand, doing 100,000 joules of work. What is the change in internal energy? Well, why don't you guys try that? Pause the video and see what you come out with. Okay, so this is a really, really simple process. Basically, you've got a gas, you're pumping 300,000 joules of energy into it, but it's also expanding, and by expanding, it is losing energy. It's doing work, and so it's losing some of that energy that you've pumped in. It's losing about 101,000 joules of that energy. So it's very simple here. You just write down the first law of thermodynamics. The change in internal energy is going to be equal to the heat that you pump in plus the work on the gas, which in this case is negative. It's the gas that's doing the work, and therefore the work is making the gas lose heat because it's expanding. So you got 300,000 minus 101,000. That ends up being 199,000 joules. Okay. All right. Okay, so we're just at about our 15-minute time limit for our YouTube videos. So we're going to go to part 2 of the first law of thermodynamics and give you another example.